We start with inductivism and positivism, and this is a position that has been developed in the 17th century by various authors in the context of the development of modern physics. This is utterly important that if you look at 17th century philosophy, most of it is developed in the context of the development of modern physics. So if you do not understand the scientific development at that time, you do not understand the philosophical positions. This is a criticism against much of, at least earlier, history of philosophy, because there were philosophers who didn't know anything about the physics going on, and then they read Descartes and stuff like that, and then they interpreted it. And if you don't know what the background is in mathematics and physics at the time, then you don't really understand what's going on. So the background here of inductivism and positivism is the development of natural science, starting there, with a conventional beginning in the beginning of the 17th century. All right. I give you first the basic idea of inductivism, what it is all about. This is something you really should know. The basic idea is that, first of all, a descriptive thing, we find singular statements and general statements in science. Now, the background is, as I said, the developing physics. You find general statements and singular statements. Now, singular statements, now I take an example from economics immediately that you feel more at home. Economic growth in Switzerland, annual variation of GDP in percent, was 0.9% in 2015. So that's a singular statement. It's about a singular fact, namely what was the economic growth in Switzerland in 2015. That's one thing, and the statement is it was 0.9% in 2015. Now, very often singular statements express observable and or measurable facts. And that's, of course, completely true for physics at that time. The singular statements were about some experiment and the outcome of the experiment that you could immediately observe. And then you said, in this particular experiment, the pressure I measured was such and such, or the volume I measured was such and such. Singular statements. In this case, in the case of singular statements, it's easy to verify the statement. Verifying meaning to confirm the truth of the statement, right? To show that the statement is true. So if you claim that the pressure is such and such, then you measure the pressure, and then you find it out, you observe or measure it, and then you will know. Because it's a singular fact. It's just one thing. You have to confirm that. All right? Now, there are not only these singular statements, but there are general statements in science, and of course also in economics, and they come under very different names: laws, theories, general hypotheses, regularity, models, also equations, and all sorts of things. And they are general. They are not concerning a singular particular fact of the matter, and they cannot be verified in the same way. Why not? Because they typically refer to indefinitely many facts. So if you have the law, say, of free fall, which every economist knows because everyone has read Milton Friedman, and he's a specialist on the law of free fall, then you know that the law of free fall is applicable to all cases of free fall on the surface of the Earth, and also with a different constant on the Moon or on Mars or wherever, right? So if you want to know whether the law of free fall is true, whether it's a true statement that it contains, then it's not enough just to look at one case, but you've got to look at all the applications. And there are, unfortunately, of course, indefinitely many. So it's a tricky thing that you say, oops, singular facts, they're fine, but how to confirm these general statements? And you need these general statements because science, modern science, physics in particular, is about general statements. It's about laws, about models, about theories. Paleontology is also about singular facts, but physics, especially all the laboratory sciences, are about these general things, theories, hypotheses, and so on, as is economics, right? So the question is, or the problem is, this is just an elaborate term here, the epistemic status, meaning that how do I confirm it? You know, how can I know it's true? That's episteme is knowledge, and the epistemic status means with respect to knowledge, how about these general statements? And that's problematic because it's not obvious how you can find out that a general statement is true, or at least approximately true, all right? So, for instance, again, for you an example, law of demand. When the price of a product decreases, its demand increases. That's a very general statement. And the question is, how can we verify that? You know, one instance, two instances? Is that enough? Is that good enough? Well, nobody knows. How can it be confirmed as it applies to infinitely many cases? That's the problem, all right? And that problem was seen very clearly then in the beginning it was not seen that clearly, but then later it was seen very clearly. And the point is now that a position that is called inductivism, there it is believed that we can gain these general statements by what is called inductive generalization from confirmed singular statements. So what you do is, that's the idea of inductivism, right? This is where the name comes from. You have singular statements, a few of them, or many of them, we'll see that, and from them you somehow infer to the general statement. Right? So you observe the law of the free fall a couple of times, and then you measure it, and then you say from there we can somehow generalize to the general case. Right? Sounds a little risky, is risky, but this is what is called inductive generalization. Generalization is clear because you go from the particular to the general, and that this specific way of generalizing, it's not deductive logic, but it's inductive logic. It's also an old name. Don't care about the name, it just means this sort of generalization to yet unknown cases, right? This is the risky part, right? You have the known cases, you measured it, but you're generalizing also to unknown cases. And the question is, does this work? Or is that tricky, or what's going on here? Okay, so this is inductivism. Now, inductivism now states that scientific knowledge is gained in a two-step process. And the first step is that you carefully observe singular facts without any theoretical prejudice, which is called, in modern philosophy of science, that's called theory-free facts, right? You observe the facts, and you don't put any theory in it, but you just say, what's the case? Let's observe it, and then you find out that and that is the case. You measure it, and then other people look as well, and then you say, yes, we measured the value 0.14 or whatever, right? And so what you do in the first step is you carefully observe these singular facts and you articulate them in singular observation sentences. You write them down, right? Very simple. You write them down. I measured, this value, this variable has the value such and such. Now, these facts are often called data, right? This is the usual way how scientists speak about data everywhere in all the sciences as far as I can see, or positive facts, right? And a position that starts with positive facts is often called positivism. So positivism is a position that emphasizes that science should begin its enterprise with stating positive facts. And so if you also in the derogatory sense, when someone says, oh, that's only positivism, or that's very positivistic, that means that person is too strongly committed to the facts alone and not to some sort of theorizing. So this is, of course, you can't know that if you don't know the history of all that stuff, but this is the meaning here of positivism, starting with positive facts, and positive that comes from the Latin ponere, and that means, well, in a sense, also establish, right? Established facts, right? So inductivism also then is often called positivism. Now, this is only the first step. Then you have a set of facts, singular facts, but you want to get to theories and models and so on. And then you have to generalize from the data to general hypotheses or laws or theories, models, whatever you have. And that's the tricky step. That's the step called inductive generalization. This is important for economics. We'll see that in chapter 6, I think, of this lecture class when we talk about models. And Sugden, a theoretician in economics, says it's the step from models to reality is an inductive step. And we'll see whether that works. So this is still an important thing, and all scientists have in the back of their mind inductive procedures, meaning somehow generalizing from singular facts. Now, the point is now that the question is under which conditions can we really generalize? You know, we have a few facts, or maybe even 1,000 facts, and if you generalize to potentially infinitely many, that's somehow a risky step. I mean, how can you know that you are right? So that seems to be somehow tricky, and the general consensus in inductivism is, roughly speaking, that this inductive generalization is allowed if the number of data is large. So you have many data points, right? Not just 2 or 3, just not prejudices and then generalization, but you have many of them, and they are gained under sufficiently varying conditions. So if you want to, for instance, generalize from, you've seen 3 white swans, and then you want to generalize to all swans are white, and then you go to the Zurich Zoo and you see all the white swans, you see 15, say, wonderful, that's enough, I generalize all swans are white. Well, I don't know whether the Zurich Zoo has black swans as well, but they are in Australia anyway. So you should walk around a little and look, at diverse data. If your data set is much restricted, your generalization may be wrong, right? And therefore, you must have diverse data gained under sufficiently varying conditions. And then finally, which is almost trivial, none of the data contradicts the intended generalization. So once you have observed one black swan, you're of course not allowed, even if you have observed 850 white swans, still to say all swans are white. Of course not. So this is the essence that can be elaborated, but that's not important here. That's the essence. And that sounds pretty pragmatically plausible, right? That you say, of course, if I want to generalize in that way, I got to have enough data, and the data must be diverse, and none of these data points must contradict my general hypothesis. Yes, and this is the way we do it. And then you look at the practice, what people say did in the physics of the 17th century. Yes, they proceeded that way. They had laboratory conditions and made experiments, and then they generalized in this way. Okay? So, there are examples that represent a fundamental problem of inductive generalizations, and that's a problem that all the sciences do confront, and I show you that problem. So, with one example, first of all. Imagine someone falling from the top of the Empire State Building, and he or she is quick enough to count the stories he or she is passing, and then the person says, I fell 20 stories, 40 stories, 60 stories, 80 stories, no problem, right? No problem. Yes, I don't know, Empire State Building, how many stories it has, less than 200. So after 80 stories, it's very, very fast. That story in the other end comes to an end. So the point is, this is perfectly okay. The person says, I've seen so many stories, one after the other, nothing happened, so why shall there ever be anything happening? And you see here, there is some sort of problem here. In this situation, you are not allowed to inductively generalize. Because you're getting a false conclusion. So, and this person will not suffer from the false conclusion. It will suffer from other things, all right? So, another one is now much nearer to science, for instance, is that you are interested in the properties of wax, for instance, and then you say, my measurement of the melting point of wax consistently gave the result of 54 degrees, and then you generalize, so all wax will melt as 54 degrees. The fact is that it doesn't. Wax is not such a homogeneous entity, a substance that it melts all at the same thing. But you may have, with a selection of wax samples, you may get this result. So the point is here that you have a problem that sometimes inductive generalization seems to work, and there are obvious cases in which it doesn't work. And as a scientist, of course, you must distinguish which is which. Yes. First, let's see the diagnosis. Why is that so, that in these cases that do not work, the answer is here, these examples, they are not something like natural laws or something like that, something solid, but they are something which is called, in philosophy of science, they are called accidental generalizations. There are generalizations that happen to be true for a particular situation, but not beyond that situation. So for instance, the standard example in philosophy of science, if you have some coins in your pocket and you say, all coins in my pocket are made of copper, for instance, right? That may be true. But this general sentence, all coins in my pockets, is just an accident that they happen to be all of copper. It's not a law that the coins in your pocket are made of copper. It's just a general sentence that happens to be true, but it's accidentally true. So this is called an accidental generalization, and one have to be careful with inductivism that one doesn't end up with accidental generalizations, because they have counterexamples, right? Strong counterexamples. So inductive generalization seems to work if it hits a natural law, a regularity apparently based in nature itself. For instance, Galileo's law of free fall. That seems to be valid on Earth. And if you have many examples of the law of free fall, and then you have many examples where you measure time versus a distance, and then you generalize it to the law of free fall, it's fine. Why? Because the general statement is indeed something like a natural law, and therefore it works. Whereas when you have 3 times only copper coins in your pocket, you can't generalize to the 4th time because it's an accident that these facts obtained. And therefore, the point is inductive generalization, must hit something like a natural law, some regularity that's in the things and not just by accident. So the question is how to tell the difference. So if you have a certain situation, things are the same, like falling down Empire State Building or having observing the law of free fall, how can you tell one from the other? Because in one case, inductive generalization is okay. In the other case, it's not. How to tell the difference? Now, in the 2 examples that don't work, about wax and about falling down Empire State Building, more variation of the condition is necessary in order to see that the generalizations are not laws. You need in the Empire State Building more stories, and in the wax case, you need different kinds of wax. So the condition that I mentioned, under which condition the generalization in inductivism is valid, it's really the variation of the conditions under which you observe. And that must be radical enough, right? If you have a restricted base of data concerning the variation of the conditions, then you are in danger of generalizing to something that's not generalizable, right? And this must be avoided. So this is the problem that the inductivist position has, or that inductivist people following inductive procedures have. Now, this has been more or less confined to the natural sciences. Now, how about the social sciences? When we go to the social sciences and we want to apply inductive generalizations, that means what we need that induction works is we have to have some sort of similar to natural laws. We have to have laws, otherwise the generalizations don't work. So, do we get by inductive generalization in the social world accidental generalizations, right? Something that by accident happens to be the case, or do we get something like a natural law, a regularity that's somehow rooted in the nature of society, or whatever that then is, similar to a natural law? For instance, I give you here examples which are real-life examples. Data may suggest a functional dependence of macroeconomic variables. So if you have macroeconomics, this is all what you want. You want to have dependencies of macroeconomic variables. And then, once you have such a functional dependence, is that an accidental generalization that may not be projected into the future, or is it something that may be projected into the future? Right? You have, for the past, you have this correlation, and then you ask yourself, can I build a policy on that? Let's assume it's really causal, or it's plausible that it's causal, and then you say, can I build a policy on that, changing one of these conditions, and then I know what's going to happen, because we have here something that can be projected into the future. Or does the functional dependence indicate a robust, if it's not projected, or does it indicate a robust causal relationship that may be projected into the future, ceteris paribus, of course, excluding contravening causal influences. So this is a little vague, but anyway, this is the idea. Here's an example. Take Okun's law. Or perhaps, it's not clear that it is a law, so perhaps law. I don't know. Anyway, so these are the data from the United States. After the war until, I think, 2016. This is the quarterly change in the unemployment rate, and here you have the quarterly change in the GDP growth. So it's 2 differentials, and what you find here, these are the points for the quarters, and that what you find is you've got a wonderful regression line here, and that seems to be, roughly speaking, that is a sort of regularity going on here, which has also some plausibility that the change in the employment rate has something to do with the change in the GDP. It's not implausible. Then you have these wonderful data. You can have it for different times and different countries. You find them in the internet. Many of these data here. And then you say, well, it's even called a law. And then what you say, of course, when you state Okun's law, what you say, you can give the slope and then you can write down the equation. Then you may say, yes, we have inductively generated that law. Now, the question is, given the discussion of inductivism, is that really a law? Is that something that's, so to speak, deeply built into the economy, such that under all the circumstances we get this dependency, or don't we do it? Is it just an accident that for 50 years it was valid and perhaps in 100 years it's not valid any longer? Yes, please. This is a statistical law. Of course, it doesn't have to be a deterministic law, but you can say this is a law in the statistical sense. So it's not strict, it's statistical, so you've got to be a little liberal here. Well, not liberal, but tolerant here. It's not a deterministic law, of course. Yes, that's the problem, how to falsify the statistical, under which conditions would you give it up, right? There are statistical measures for that, but that's a problem everywhere where you do statistics, be it medicine or be it economics or be it other disciplines or demography or whatever it is. Whenever you have these statistical connection, also even in physics you have these statistical things, and then you have to deal with it, and people have developed methodologies for that. Okay. So yeah, it would be wonderful if there was a wonderful economic deterministic law. I would have taken that as an example, but this is the best we get in economics as far as I can see. And it's even called a law, right? Now, similar with respect to economic development, can we inductively gain more than accidentally existing trends whose dependence on exogenous variables is unclear? This is, of course, the case anyway. The dependence on exogenous variables is unclear, but the point is, are we now, with Okun's law, are we at something that's really law-like, or is this just an historical accident over these 60 years? It's only statistical, and especially you can then develop these points which are very far from the regression curve and say, oops, wow, can you really say it's a law? Well, this is how the situation in economics, and where you are confronted with that question of inductivism. Do we get something robust like natural laws, or do we get accidental generalizations only? All right. Now, this is a remark that's not immediately relevant for you, not immediately, but indirectly it's relevant, because when philosophers usually discuss the problems of inductivism or inductivism, they discuss a problem that's different from the one I discussed. And there is no consciousness, neither as far as I can see in economics, nor really in much of philosophy, that there is a difference between two problems of induction. One that the philosophers discuss, that the scientists usually don't care about, and the problem of induction, how scientists discuss it, that was the way I discussed it before. That's the question I want to inductively generalize, and the question for the scientists is, under which conditions am I allowed to generalize? That's one question. And the question that is discussed in philosophy as the problem of induction, since David Hume from 1739, is not exactly the same as the problem I discussed here. And you should see that there is a difference. We'll see that also then in the discussion on Sugden, that Sugden doesn't see that there are really two different problems, and you cannot infer things from one problem to the other. So it's very important. Now, the question that philosophers ask is a different one than the one I just gave to you. In philosophy, the question is, what is the justification of inductive inference in the successful cases? Right? You have a successful case, right? Say the case of the law of free fall. That seems to work. We have no indication that the law of free fall is invalid on the earth. But still the question you can ask is, why does this inductive procedure work? How come that it works, right? It's a generalization from known cases to unknown cases, and you can say, how can you be sure that it will work for the unknown cases? So it's a question of the justification of the inductive step. So in science, the question of induction usually is, how can we practically distinguish valid inductive inferences, whatever their justification is, from invalid one? So a physicist doesn't ask, well, how does that step really work from these cases, simple cases, where something falls to the earth, and then to the law of free fall. What's the logical relationship there? Because scientists are happy when something works and when they have control over the working. And then they don't ask the question, what's the deeper justification for it? Because that's useless for their scientific practice. And then scientists usually don't ask useless questions. They simply say, I want to inductively generalize, so let's see in which cases I am able to and in which cases I shouldn't do it. Whether the philosophers ask here, what is the logic, as philosophers then call that, behind that justification? And then they ask this question. So the scientists want to practically distinguish valid inductive inferences from invalid ones. And the difference, as I said, of these two questions is not always appreciated, and we'll see that later in section 6. So if you're interested in the question of induction, how the philosophers discuss it, then I refer to an article by Leah Henderson, also in the Stanford Encyclopedia of Philosophy, The Problem of Induction. There you get everything you want to know about what the philosophers deal with. But as I said, it's very important, and it's completely, as far as I can see, underappreciated in discussions about inductivism, that this is not the questions that scientists usually have, including economists. No scientist is generally interested why the functioning, the cases in which induction works, why it works. They're happy to identify that it works. And the deeper philosophical issue then is, forget it, leave it to the philosophers. All right, so this is the point of inductivism. As I said, inductivism has been around for more than 400 years. People are familiar with it. People know that it's somehow problematic, but now and then it appears in economics, so you should know that it exists. And that's a good point here now to make the break. Inductivism hasn't, to my knowledge, been broadly discussed by economists, whether it's appropriate or not, which is different from the following three positions, which have been broadly discussed. And I will tell you also something about the reception by economists and their stances towards these different positions.